Hi, my name is Yona. I'll be presenting our paper, Decision Making Under Miscalibration. This is joint work with Guy Rothblum, and unfortunately I couldn't be here in person, so apologies in advance. Okay, so the setting we study in this work, we call it From Predictions to Decisions. By predictions, I mean that we have a universe of individuals X, and some risk predictor, which is a mapping from X to values in the interval 0, 1. For example, to estimate the risk of a cardiovascular event in some follow-up period. By decisions, I mean that the way we intend to use P is to inform multiple downstream binary decision problems. For example, whether an individual should be prescribed a medication or be given a certain medical treatment. So we treat this in a utility-based framework. Basically, we assume we have some distribution over individual and outcome pairs, a risk predictor, as I mentioned. A treatment threshold is just some number j in the interval 0, 1, where we understand that someone receives the treatment if their prediction is higher than this value. And a downstream decision problem is basically parameterized by its cost structure. So think of it as the relative costs of making correct versus incorrect predictions. So overall, all of these components define a utility from thresholding P at a threshold J. And we will say that a treatment is harmful if this utility is actually lower than what we could have obtained without having used a predictor at all, right? We can always just decide to treat everyone or treat no one, and that gives us some sense of utility as well. Okay, so for us, the decision-making problem is basically given the cost, the distribution, and the predictor, how should we choose the treatment threshold J? And an existing but partial answer to this question is that whenever the predictor is perfectly calibrated, then there is a threshold that I'll denote as J star, and in the literature it's known as the therapeutic threshold, which guarantees no harm in this case. And the interesting property about J star is that it does not depend on either the distribution or the predictor at all, only on the cost structure of the decision problem. And here, the perfect calibration requirement is basically saying that for every possible risk value V, if we look at all the individuals that received a prediction of V, exactly V fraction of these actually have positive outcomes in the true distribution. Unfortunately, this result breaks down under miscalibration. So for example, in this previous work, the authors used simulation studies to show that whenever they induce miscalibration to a calibrated predictor P, eventually it makes treating at this therapeutic threshold actually harmful in the sense that I've defined before. So let's start gaining some intuition for how decision-making might look like under miscalibration. So suppose that the therapeutic threshold here is 0.05. Intuitively, this means that I anticipate a much greater benefit from identifying true positives than having false positive predictions. And consider the subset of women who receive a prediction of 0.04. Should I treat these or should I not treat these? So if I knew that my predictor was perfectly calibrated on this subgroup, then I know that I should not treat them. But what happens under miscalibration? So I could still use J star and not treat them. But then if my predictor was underestimating the risk in this population, I might regret not treating them. But on the other hand, if I use a lower threshold and then find out that my predictor was overestimating the risk in this group, then I might regret treating them. So overall, we have these competing concerns, and it's not a priori clear how to balance them, because the impact of the errors that I can have within a certain bound of a miscalibration errors don't have symmetric effects because of the kind of asymmetric nature of this binary decision problem. So our work is motivated precisely by this question of how do our decisions impact protected groups. And there's actually a lot of work showing that this is really an issue in practice. For example, This work discusses how the commonly used Framingham risk score for cardiovascular risk overestimates the risk in women, which indeed causes a harmful model if you use it for thresholds 20% or higher. And you might ask, okay, maybe what we need to do is we need to just upfront ensure that our predictor is multi-calibrated. Well, this is important, but it doesn't completely solve the problem, because as long as we have a finite number of samples and a rich class C, where we can bound the worst case calibration error, there are still going to be some calibration errors that are just inevitable. So we don't escape this problem completely. So the perspective that we put forth in this work is basically, if J star, the therapeutic threshold, is the optimal threshold to apply to a perfectly calibrated predictor, irrespective of the distribution and the predictor, is there a similarly optimal threshold that we should be applying when we're faced with an imperfectly calibrated predictor? Okay, and while this kind of compiles, it does suggest several natural questions. Most importantly, which solution concept should we use to determine optimality here? And then what does this threshold end up looking, and is it actually different from J star? So I'll give an overview of our results. Basically, to determine the solution concept, we define a notion of regret under bounded miscalibration, and we propose that you should use a threshold that is minimax optimal, that minimizes the maximal regret that you can obtain. Technically, we show that you can actually obtain closed form expressions for this threshold under different ways of measuring miscalibration. These end up having very simple expressions, and these reveal that this threshold actually ends up being different from J star precisely for decision problems that have very asymmetric costs. In some sense, this gives a formal and rigorous explanation for a behavior that's actually quite intuitive, which is, if you're under uncertainty because of the miscalibration and the problem is asymmetric, then in some sense you should be conservative. So to summarize, we showed that even slight miscalibration might require you to take this miscalibration into account and change how you translate predictions to decisions. Our solution concept is just one choice. It's very worst case in nature. And I think an interesting question for follow-up work is whether by building in additional assumption, the effect of miscalibration ends up being maybe different in interesting ways. And I think more broadly, thinking of algorithmic decision-making not as a one component, but as a pipeline problem is interesting because it opens up this question of how do the different stages impact each other. For example, maybe it suggests useful desiderata for the earlier stages, like we did here with multi-calibration, but maybe it suggests that we should have a different behavior for the subsequent stages, depending on what we anticipate went wrong in the beginning of the pipeline. That's it. Thank you very much for your attention, and happy to discuss offline. Thanks.